So electronegativity, again, something we can link to the periodic table, which I think we probably will do shortly. But electronegativity. So definition of a covalent bond. Again, there are a few definitions out there. They do differ amongst exam boards. Some of them are given to you in your exam board specification, so check. But a covalent bond is a strong electrostatic attraction between a shared pair of electrons and the nuclei of the bonded atoms. Something along those lines will work perfectly. The key is that it's the strong electrostatic attraction between a shared pair of electrons. Okay, so that's a good key point. That's why we put it in bold. And the nuclei of the bonded atoms between them. Or around it, sorry. So learn it if you can. Learn that definition, or learn the one from your textbook, but be aware that there are differing ones out there and on the internet. Just learn one and just keep reminding that one. When you come to do an exam question, don't Google it and use a different one. Use the one that you've been trying to learn. Make sure you're only learning one thing when you need to. But yeah, so what's happening in covalent bonds? Why are we talking about electronegativity? Well, if we've got, let's go back to blue. If we've got HF, so just as we've got this diagram here showing us our electron-rich region and our electron-poor region, if we draw HF there and show it in terms of a dot and cross diagram, our shared pairs of electrons. So dot and cross, we've already looked at this one, so I won't explain it too much. But what's actually happening? Is that exactly where the electrons can be found or not? What is this term electronegativity that Pauli came up with? We need to know the definition because we need to be able to give it in an exam. So electronegativity is what? How do we determine it? Negativity. Just double checking my spelling. Is what? Electronegativity is the ability of an atom to attract to attract the pair of bonding electrons. So it is a pair of bonding electrons. Again, I'm going to be lazy and do E minus, but please in an exam write out the full word. In a covalent bond. You need to learn that off by heart because we need to be able to give it. But what does that mean? How does that affect things? Why does that create this electron-rich region and an electron-poor region? Let's have a think. So if they're supposed to be sharing electrons, but most of the electrons are spending, because the shared pair of electrons, between hydrogen and fluorine, are actually spending more of their time around the fluorine than around the hydrogen, then hydrogen, which has only got one proton, and so only needs to share, has got one electron that belongs to it, so is neutral with that one proton and one electron. And fluorine has got 9 protons and 9 electrons. Yes. So when it's got 9 protons and 9 electrons, it's neutral overall. So when we combine in a covalent bond, a hydrogen and a fluorine, our structure is neutral. There are the same number of protons as electrons. But fluorine has got, if the shared pair of electrons between hydrogen and fluorine actually spend more time around the fluorine because they're more attracted to the fluorine, the hydrogen is left with just its single proton. It no longer has control or exists with its electron, and so becomes delta positive, partially positively charged. That means it is an electron poor region, so it's delta positive. Fluorine has therefore got control of, or an extra electron is spending more time around fluorine than it has protons. And therefore, fluorine becomes an electron-rich region, or delta negative. Okay, so let's think about it in terms of these species. So protons in the nucleus, we've just said this, protons in the nucleus draw all of the electrons in the atom towards them. Of course they do, they're attracted. Protons are positive, electrons are negative. Therefore, as you increase protons, if you're increasing protons, you're going to be increasing the electronegativity, the ability to attract protons towards them. Protons in the nucleus draw all of the electrons in the atom towards them. So in general, and I'm saying in general because it's not an exact science, chemistry never is, adding more protons increases electronegativity. Increases electronegativity. However, and we'll think about how that applies to the periodic table in a minute. However, if we add enough electrons to fill a shell, what's going to happen? Well, our bonding electrons will be further from the nucleus. So our valence, our available electrons for bonding, will be further from the nucleus, our outer electrons. And therefore, because we've added a shell, more electrons will be shielding the nucleus. That means as you go down a group, you're increasing protons, which should increase electronegativity, but you're also, as you go down a group, increasing electron shells, which is going to reduce electronegativity, decrease electronegativity. So again, in general, this decreases electronegativity. Oops, definitely haven't given myself enough space. Let's try that again. Electronegativity. I'm so sorry for my handwriting. Electronegativity. So, which has the impact then? Again, we're thinking all of this, it's both sides of the argument, positives and negatives, advantages, disadvantages, for and against. In lots of cases, there are conflicting bits of chemistry that we have to be confident about which is the dominant factor. And I know that I found it difficult when I was doing my chemistry A level of trying to remember which is which. Here's a little hint. It's nearly always shielding. Shielding is the dominant factor, nearly always. So if you're ever unsure and you haven't got it sorted in your head, just guess shielding, because it's nearly always shielding is the dominant factor. So that will be what the trend that you see appearing. So in this case, it's the same. It is shielding. So overall, that doesn't look like a word. Let's try that again. Oops. Overall, the dominant factor is shielding. As in, that has the greater effect, and that is what trend we see. So what trends do we see then in our periodic table? As you go across a period from left to right, again, I'm just going to show that I mean from left to right. I'm trying to keep it consistent. The number of protons increases, electrons being added to the same shell, and that means electronegativity increases. Electronegativity increases across a period from left to right. What about as you go down a group then? As you go down a group, although you are increasing number of protons, you are also increasing the number of shells, which increases shielding. And shielding is a dominant factor, so we can ignore the effect of the protons and just concentrate on the effect of the added electron shells. So as we go down, electronegativity decreases. Although it is important to recognize that protons are added, and so the trend that you see is lessened by the fact that you are still adding protons as you go down a group. So if you weren't adding protons, you were just adding shells, you'd probably see a greater decrease in electronegativity as you went down a group. But because we have got additional protons as well, that decrease is lessened because the protons are trying to increase electronegativity a bit. You'd never be examined on that, but I do think it's important to recognize. One of the ways, my favorite way to remember this trend, so rather than having to remember again two different facts, the trends and what direction the trends are going in, etc. Just remember, what's the most electronegative element? You've probably been told a million times. What's the most electronegative element? Fluorine. Fluorine is the most electronegative element. So if you're looking for trends, you know that fluorine has got to be the top of the trend. It's got to be the highest. And therefore, everything must be increasing towards, across the period, it must be increasing towards fluorine, and upper group, it must be increasing towards fluorine, or it must be decreasing away from fluorine. So if you can remember fluorine is the most electronegative, I will write it out fully. reactive, then that helps you to remember the trends, because that's got to be the top, the most within the trend. Let's keep going. So using these trends, we can explain why reactivity decreases down the group. So reactivity of the halogens decreases down the group, and we can explain it using our reactivity. Fluorine is the most reactive halogen because of its electronegativity. So fluorine is the most reactive halogen, as it is the most electronegative. So its ability to grab an electron and hold on to it is means that it can steal electrons from things, so it can react as an ion easily, but also it forces things to share electrons with it loads, because it wants that bonding pair of electrons. It wants to attract that bonding pair of electrons. That means it can form stable products, and that's one of the reasons why it reacts. Fluorine is also the smallest. Why will that mean that it's more reactive? Why does being small mean it's more reactive? It means the product that it forms when it steals an electron has a very high charge density. So has greatest charge density as an ion. As you go down the group, the atomic radius is going to increase. If the atomic radius increases, charge is spread across a greater area. And halogens are trying to gain an electron when they react. So the bigger the atom is, the lower the charge density is of the anion that would be formed, and therefore linked to that, the harder it's, let me rephrase it, the attraction between the outer electron and the nucleus is going to be weaker. So you're not going to create an anion that is as stable. Okay. Did I want to say anything else? Don't think so. Okay, let's go. So let's have a go at some answers. How am I doing for time? Not too bad. Might speed up a little bit. So exemplar exam questions. Actually, no, we're doing all right. Exemplar exam questions is a short answer. By considering the trends in the properties of group 7, predict the following for astatine, stating a reason for each. So what's the question about? The context is properties of group 7. So in my head, I'm thinking group 7 properties, right? What do I know? What do I know about that? The command word, I need to predict something and state something. So my command words is state and predict. So predict, that tells me, and hopefully should reassure me, that I shouldn't know this off by heart. Because I've been asked to predict something, the meaning of the command word predict, as we looked at before, is that you shouldn't know it, but you should use the information you're given to work it out. So predict the following for astatine. I don't need to know it, but I can work it out. I have been given the tools as an A-level chemist to work it out. State a reason for each. So give a short reason for each. They don't want long sentences because it's just said state, so a short reason for each answer. And the direction, well, I've been asked about the trends in properties, so physical state of astatine being at the bottom of the group. So as the trend changes, what will the physical state of astatine, what is it likely to be? Its atomic size and its electronegativity. It says relative to other halogens. That's an important point because it hasn't asked me to predict the Pauli number for it, its electronegativity value for astatine. So I don't need to think about actual exact numbers. I just need to think about the trend because it's relative to the other halogens. So is it going to be more or less electronegative than the other halogens? Okay, so physical state at room temperature. What would you have said? As we go down the group, gas, liquid, solid, well, acetylene can only be a solid then, because iodine was, and that's above it within the trend, so it should be solid. Why is it solid? Why is it going to be solid? It's solid because we've got, and we're going to look at these a little bit more in a couple of slides time, but we've got more electrons in acetylene. That means we're going to get stronger intermolecular forces relative to the other halogens. That's our explanation. More electrons, sorry, solid, that gives us our first mark. And then the explanation, there are more electrons, so stronger intermolecular forces for the second mark. What about B? What's its atomic size compared to other halogens going to be? Well, as we go down the group, we've added shells. Yes, we've added protons, so that usually pulls the electrons in, but we've added shells, which adds shielding. Shielding is a dominant factor, so that's why it's getting bigger. So it's larger because there are more electron shells. And I'm just going to add in and more shielding, and therefore more shielding. If you want to add another layer of explanation to it, so say it's a 3-mark answer, not a 2-mark answer, you could then go on to say, and therefore more shielding. So the attraction between the nucleus and the outer electrons will be weaker or less. So if you have the marks available and you need to give complete explanations, you would go on to say more. This is just stated a reason, so I don't need to go into too much detail, and there's only 1 mark available for it anyway. So there's no point in me giving 5 or 6 layers to my explanation. I wouldn't get any more than 2 marks. Part C as well, then, explain its electronegativity. Well, again, we know the trend is decreasing electronegativity as you go down the group because fluorine is our most electronegative element. So it must be less electronegative. Why? What's going to affect its ability to attract an electron in a bond? Well, if it's miles away, it's not going to be able to attract it very strongly. The attraction between the nucleus and the outer electrons is going to be very weak because of the added electron shells. So acetylene is less electronegative as it has more full electron shells that shield the outer electrons from the nucleus. In both of these cases, C and B, so just checking A as well, but in C and B it's more pertinent. There are contradictory things that we could have said. So we could have talked about increased number of protons attracting electrons and pulling them closer. But because, again, thinking about what are they looking for, why are they asking us this question, it's only a 2-mark question. So all they're interested in is, can we explain the trend, not can we justify the difference in size or anything like that. Can we compare? We're not looking at both sides of the argument. They're only interested in a short answer, so I only need to give one side of the argument. Again, thinking about what are the examiners looking for? Why are they asking us that question?